Kinetics is the study of the rates of chemical reactions and the factors that affect them. Reaction rates run all the way from virtually instantaneous, like the reaction between H plus and OH minus in solution, to so slow they essentially do not happen, like the conversion of diamond into graphite. In addition to giving information about how fast a reaction is, kinetics studies can give us insight into exactly how a reaction occurs, that is, what the mechanism is. The rate of a reaction is defined as the change in concentration of a product with time. Because the amount of each product produced and the amount of each reactant used are related to each other, we can actually monitor the change in concentration of any reactant or product to get the information about the rate. The only difference is that with reactants, the concentration decreases, while with products, the concentration increases. The table shows the concentration of butyl chloride, C4H9Cl, as it reacts with water to make butyl alcohol, C4H9OH, and HCl. The concentration of butyl chloride was measured at certain times. Note that the intervals are not all the same. As mentioned earlier, the average rate is the change in concentration of the product with time. Mathematically, it is written average rate equals delta brackets product over delta T. The square bracket is read concentration of product, and the delta is read change in. So we read this as average rate equals change in the concentration of product over the change in time. That's the average rate over that interval. However, we are measuring the concentration of butyl chloride, so the average rate is delta concentration of butyl chloride over delta T. We calculate the rate for each interval shown. Remember that the intervals are not the same size, and in this case, we will calculate the absolute value of the change since we know the concentration is decreasing. We will talk about what the sign means and how we use it later. To calculate the rate for the first interval, we take the change, 0.0095 molar, and divide by the time interval, 50 seconds, to get 1.9 times 10 to the minus fourth molar per second. For the interval between 500 and 800 seconds, we take the change in concentration, 0.0168 molar, and divide by 300 seconds to get 0.0560 times 10 to the minus fourth molar per second. When we look at the average rate for all of the time periods, we discover that the average rate decreases as the reaction proceeds. This is nearly always true. This happens because, over time, the concentrations of the reactants decrease, so there are fewer molecules to react together to produce reactions. More about this in a later lesson. If we plot the concentration of the reactant versus time, we get a graph like this. The slope of the tangent line at a particular point on the curve is the instantaneous rate, usually for the reaction on the slides written as rate equals d concentration of C4H9Cl over dt, where the d notation is from calculus. This will be important later. Since all reactions slow down over time, the best time to compare rates is at the very beginning of the reaction. The best type of rate to compare is the instantaneous rate. If we look at the reaction and can measure the change in concentration for the production of butyl alcohol, the product C4H9OH, and compare it with the change of concentration for the disappearance of butyl chloride over the same time period, we find that the change in concentration of C4H9OH and the change in concentration of C4H9Cl have the same magnitude. This is because the two substances are in a 1-to-1 ratio. So every time a molecule of butyl chloride reacts, a molecule of butyl alcohol is produced. So the magnitude of the rate of disappearance of butyl chloride and the magnitude of the rate of production of butyl alcohol are the same. However, the concentration of butyl alcohol is increasing, while the concentration of butyl chloride is decreasing. We show this in the equation in this way. Rate equals minus the change in concentration of C4H9Cl over change in time equals concentration of C4H9OH over change in time. Remember that the rate is defined as the change in concentration of the product with time. This means that the rate is positive since the concentration of product increases. So, since the concentration of the reactant is decreasing, producing a negative change in concentration, we must use a negative sign to change a negative rate into a positive one. What happens when the ratio is not 1-to-1, as in this reaction? Two molecules of HI react together to produce only one molecule of H2 and one molecule of I2. This means that the concentration of HI decreases twice as fast as the concentration of I2 increases. So, if we were to measure the rate of the reaction using HI, we would get a number twice as big as if we were to measure the rate using I2. To make the two rates equal, we would need to either double the rate using I2 or multiply the rate using HI by 1/2. Because the 2 in the fraction is the coefficient of HI, we choose the second method. For the general equation, A molecules of substance A react with B molecules of substance B to produce C molecules of substance C and D molecules of substance D, where the lowercase letters are the coefficients and the uppercase letters are the substances, we would have the following relationships among the rates of the reaction determined by using each reactant and product. The rate is equal to -1 over A times the change in concentration of A over the change in time, which is equal to -1 over B times the change in concentration of B over the change in time, which is equal to 1 over C times the change in concentration of C over the change in time, which is equal to 1 over D times the change in concentration of D over the change in time. Note that the two reactants are negative, as are all reactants, while the two products are positive, as are all products. Also notice as well that each change in concentration over the change in time term is multiplied by 1 over the coefficient of that substance in the balanced chemical reaction. Factors that affect reaction rates. There are 4 general factors that can affect the rate of a reaction. They are, number 1, the nature of the reactants. This involves many things. Because bonds are being broken and new ones formed, the energies of those bonds are significant in determining how fast the reaction occurs. In addition, the physical state is important, since molecules must come into contact with each other for the reaction to occur. The more homogeneous the system is, the faster that can happen. The surface area is significant for heterogeneous reactions. The surface area is sometimes listed separately. Other things that come under this factor would be things like the shape of the molecules and the number of bonds that need to be broken. Number 2, the concentrations of the reactants. As the concentration increases, the molecules collide more often. The more collisions there are, the more likely the reaction. The pictures show steel wool glowing in the heat of a flame in air on the left, but actually flaming, a faster reaction, when placed in pure oxygen. Number 3, temperature. The higher the temperature, the faster the molecules move, and the more energy the molecules have. So molecules collide more often with greater energy, and the reaction is more likely to happen. Number 4, the presence of a catalyst. Catalysts are substances that speed up a reaction without being consumed by the reaction. This means that there is the same amount of the catalyst present after the reaction is over as there was before the reaction began. The catalyst affects how the reaction occurs, changing the mechanism. We will learn more about these factors when we study collision theory.